In this lesson, we ask the question, how does the temperature of a gas affect its pressure? So we're going to change the temperature of the gas and measure the pressure and see how the temperature change affected the pressure change. To do this in a fair way, we have to control the other variables, volume and amount of gas. Remember that the temperature of a gas is a measure of the average kinetic energy of the gas molecules. So if the temperature is higher, the gas molecules move faster. Notice how in the simulation, as I add heat, the gas molecules move faster because their temperature rises. Remember that pressure is a measure of how much the gas molecules hit against the sides of its container. A gas which exerts more pressure hits more against the sides of its container. Now, what do you think will happen as the temperature rises? Will the gas molecules hit more or less against the sides of the container? Notice that as the gas molecules move faster, in other words, as the temperature of the gas rises, the molecules hit more and more and more against the sides of the container. The pressure of the gas increases. Now, the simulation also has a thermometer to measure temperature and a pressure gauge to measure pressure. So let's run the simulation again and notice what happens as the temperature rises. Notice what that does to the pressure gauge. As we add heat to the gas, the thermometer reading rises and the pressure reading rises. Here is some actual data collected from a laboratory experiment like this. Notice that as the temperature increases, the pressure increases. Does this mean the temperature and pressure are directly proportional? Remember that direct proportion means that as one variable is increased, the other variable also increases by the same factor. So let's look at this data to see whether this is true. Let's just look roughly at lines 2 and lines 3 and notice that the temperature has approximately doubled, but the pressure has not anywhere near doubled. So from this we can see that temperature and pressure are not directly proportional if we use the units we're using here, degrees Celsius and kilopascals. But let's convert temperature into the SI unit, Kelvin. We do that by adding 273. Add 273 to each of those numbers and you find these answers. Now let's check whether temperature in Kelvin is directly proportional to pressure. So let's take lines 2 and lines 3 for example. By what factor have we increased temperature from 288 to 304 Kelvin? How do we find that out? 304 divided by 288 equals 1,05. That means 288 times 1,05 is equal to 304. Now, by what factor has the pressure associated with those temperatures increased? 111 times what equals 116? Again, we can find that out by 116 divided by 111. The answer is 1,04. So we can see that we've increased temperature 1,05 times, and as a result pressure has increased 1,04 times. Now remember, this is real data. This is not idealized data, and so there is some experimental error, so we would expect that these factors would not be perfectly the same. But it suggests that, in fact, if we could have got rid of the experimental error, the factors would have been the same. In other words, that temperature and pressure are directly proportional as long as you measure temperature in Kelvin. Now, why should it be that temperature is directly proportional to pressure only in Kelvin? Let's use an analogy to help us understand this. Imagine that you're standing on top of a building. This building is 273 meters high. You throw a ball to a height of 10 meters above the top of that building. And then you throw a ball 20 meters up from the top of that building. Did you throw the ball to double as high the second time as the first time? 20 is double 10, but is that ball double as high from the ground as that ball? Of course not. You see, when we say the ball is 10 meters up or 20 meters up from the top of the building, we are using a reference, the top of the building, which is not the real reference. So we can't compare the ball's real heights just by looking at those numbers 10 and 20. We must use the real reference, the ground, to be able to see how much higher they really are compared to one another. And in a similar way, when we compare 10 degrees Celsius to 20 degrees Celsius, when we're comparing the numbers 10 and 20, we're not comparing them against the real reference point of nothing, because 0 degrees Celsius doesn't mean that there's no kinetic energy in the molecules. 0 degrees Celsius is simply the melting point of water. It's when ice melts into liquid water. And ice already has quite a lot of kinetic energy. Just like the balls at the top of the building have quite a lot of gravitational potential energy. It's not that they have nothing. In a similar way, at 0 degrees Celsius, the molecules have quite a lot of kinetic energy. It's not that they have nothing. And so it's an artificial zero. Whereas in the Kelvin scale, the 0 Kelvin value is a real zero. It's called absolute zero, and it means that at that temperature, the particles don't vibrate at all. So 20 degrees Celsius is not double as hot as 10 degrees Celsius. Instead, 293 degrees Celsius is double as hot as 10 degrees Celsius. In other words, the particles at 293 degrees Celsius will have double as much kinetic energy as those at 10 degrees Celsius. Obviously, the number 293 is not double 10, so that's why we don't use the degrees Celsius scale when we're dealing with temperature in science. Instead, we use the Kelvin scale, and a temperature of 20 Kelvin is double as hot as a temperature of 10 Kelvin. In other words, the particles of a substance at 20 Kelvin will have double as much kinetic energy as those at 10 Kelvin.